In real life, most regression problems involve more than one independent variable. If each independent variable is linear with y, then the regression function is this. Epsilon here is the unsystematic variation. We need to estimate the coefficient beta naught, beta 1, beta 2, etc. So let's call the estimates b naught, b1, b2, and etc. up to bk. For the ith observation with b naught, b1, b2, and etc., we can calculate or estimate the corresponding value of y, and we call it yi hat. Here are some basic commands in R. To train a model, we use the LM function. LM stands for linear model. The first argument is the formula for regression, and the second argument is the data. Once we have a trained model, we can use the summary function. Given the model, it would show the results. Some other useful functions include coefficients. Coefficients give the model coefficients. Confint gives the confidence intervals for model parameters. Fitted gives the predicted values, and residuals give the residuals, just as its name says. Now let's have an example. Consider the dataset pi sales. The dataset provides data for 15 weeks of sales for pies. The price of the pies and the amount spent on advertising. After loading data into a data frame in R and exploring data, we build a regression model. Basically, we call the function LM and give it the formula for regression. In the formula, pi sales is a function of price and advertising. Once the model is trained, we use the summary function. Give it the model. The summary function returns the result as you can see. In the coefficients section of the result, we can see the estimates for all the coefficients, standard error, t-value, and p-value. Looking at the p-values for price and advertising, we can see that the p-values are less than 5%. And we can reject the null hypothesis and say that there is a linear relationship between price and sale and advertising and sale. Now we talk about residuals. Just like with simple linear regression, the residuals measure how far off the fit model is on the actual data. Given a model, we call the residuals function. And also, just like with simple linear regression, we can use the fitted function to find the predicted values given a model. We can indirectly get the residuals by taking the sales minus the fitted values. The direct way to get the residual is still to just use the residuals function. To predict the target values for new instances, we use the predict function. This OR example shows we created a data frame and added 3 instances to the data frame, and then call the predict function to predict target values for those 3 new instances. If you don't use the predict function, you can also get this directly by extracting the coefficients from the model. So we extract the coefficients using the coefficients function, and then taking the sum product of the coefficients and the instance. The result should be the same. For multiple regression, R-squared, or the coefficient of determination, is determined the same way as it was for simple linear regression, which is equal to regression sum of squares divided by the total sum of squares. When we add a new variable to the model, we lose a degree of freedom. However, R-squared never decreases, and this is a disadvantage. Here we come up with another measure called adjusted R-squared, which is adjusted by the number of variables. Adjusted R-squared is smaller than R-squared and is useful in comparing between models. For testing the significance of the overall model, we use Ttest. Ttest is to test if there is a linear relationship between all the x variables together and y. The null hypothesis is that there is no linear relationship at all, meaning beta 1 is equal to beta 2 is equal to beta 3, etc., and is equal to 0. The alternative hypothesis H1 is that at least 1 beta I is not equal to 0. Going back to the pi cell example, the p-value for Ttest is about 1.2%. So here we reject the null hypothesis. The Ttest is used to determine if there is a linear relationship between individual variables and y. The null hypothesis is that for the jth model, beta j is equal to 0, meaning there is no linear relationship. The alternative hypothesis is that beta j is not equal to 0, meaning there is a linear relationship between xj and y. And the p-value tells if the coefficient is significant or not. The confidence interval for the population slope beta j is bj plus and or minus t alpha divided by 2 times sbj. In this formula, bj is the estimate of the jth coefficient of the jth variable. T is the t-value. SVJ is the standard error. If you go back to the result showed by the summary function in the pi cells example, then plug in the values for bj, t alpha divided by 2, and sbj. We can form a 95% confidence interval. In R, you can do this directly using the confind function by giving it the model, the variable name, and the level, which is 95%.